Let's dive straight into the heart of the mystery. Stephen, why does uncovering the universe's ultimate blueprint matter so deeply? Recently, a mind-bending cosmic experiment, echoing the famed double-slit experiment, has captivated the scientific world. Astonishingly, it suggests that the very act of observing the universe through our telescopes might be reshaping its past. This revelation has sent shockwaves through astronomy. How can present-day observations reach back and influence what has already happened? Researchers are realizing that as we look deeper into time, even all the way back to the Big Bang, our current measurements may be selecting a single thread from a web of countless quantum possibilities. It's as if the universe is constantly emerging from a cloud of potential, becoming real in part because we are watching it unfold. Enter John Wheeler, a towering mind of 20th century physics. Collaborator of Einstein and Bohr, mentor to today's leading physicists, and the visionary who coined the term black hole, Wheeler explored the farthest reaches of space, time, and quantum mechanics. After decades of foundational discoveries, from atomic physics to cosmology, he turned his curiosity inward, contemplating what he called ideas for ideas. Within this collection, Wheeler confronts a perspective that challenges everything we think we know about reality. Reflecting on his own life, he once recounted, "I had a heart attack on January 9th, 2001. I knew it was a signal." With his mortality in view, he focused on a single profound question: why does anything exist at all? Wheeler believed the answer hinges on one of the most astonishing features of modern physics. According to quantum mechanics, our observations don't just reveal the universe, they shape it at the deepest level. Wheeler envisioned the universe as a vast feedback loop, one in which our conscious acts participate in the creation of not just the future, but the past itself. To make this tangible, he undertook an extraordinary experiment, a cosmic-scale version of the double-slit experiment. The results were nothing short of shocking. His findings demonstrated that looking at distant objects through a telescope could actually alter their history, revealing one specific universe out of an array of possibilities. To truly grasp the wonder of this, we need to explore this cosmic double-slit experiment. And first, it helps to understand the classic version that inspired it. At the heart of matter lies a strange duality. It behaves both as a particle and a wave. In the classic double-slit experiment, physicists shoot photons, tiny packets of light, through two narrow openings. When a detector is placed to track which slit each photon passes through, the results are simple and predictable. Two bars appear on the screen, marking the paths of individual photons. But when the detector is removed, the universe seems to play a trick on us. Instead of two clusters of dots, the screen reveals a mesmerizing pattern of alternating light and dark stripes. This interference pattern is something only waves could create. Without observation, each photon appears to pass through both slits simultaneously, as if it were a tiny ripple splitting and weaving through two channels at once. But when the physicists reintroduce the detector, the photons behave like ordinary particles again, choosing a single path and never both at the same time. The double-slit experiment captures the uncanny strangeness of nature. The outcome depends entirely on whether we watch or not. But John Wheeler took this mind-bending idea a step further, stretching it across the cosmos. And what he revealed is even more astonishing. While the classic experiment shows how observation affects a particle in the present, Wheeler's cosmic version suggests that our current observations can influence events that happened billions of years ago. To picture this, imagine a distant quasar, an extraordinarily bright beacon at the heart of an early galaxy, send out streams of light, or photons, across the universe. Between the quasar and Earth lie two massive galaxies. As we know, the gravity of such giants bends light, acting almost like lenses. In Wheeler's setup, these galaxies replace the double slits, while the quasar provides the photons. If astronomers on Earth point their telescopes at one of the galaxies, they detect photons that passed by that specific galaxy, like watching a photon choose a single path. But if they cleverly arrange instruments to collect photons traveling along both routes simultaneously, they recreate the wave-like interference pattern on photographic film, just like in the lab-based double-slit experiment. Here's the truly mind-blowing part. The quasar might be billions of light years away, so its photons arrive one at a time, barely touching the film. Yet, even under these extreme conditions, the striped interference pattern emerges exactly as if each photon knew whether it would be observed. It's a cosmic-scale demonstration that the universe, and even its history, can be shaped by the act of observation. What this means is astonishing. A single photon, unobserved by a telescope, can travel both routes toward Earth, even if those paths stretch across billions of light years. And the truly mind-bending part? By the time astronomers decide how to measure it, whether to pin it to a single path or let it follow both simultaneously, the photon may have already been traveling for billions of years, long before life even existed on Earth. In essence, the choices we make now shape the photon's history. Pointing the telescope one way creates a past in which the photon traversed both galaxies. Choosing differently retroactively forces it onto a single path, even though that journey began eons ago. The photon's path isn't fixed until the moment we decide how to measure it. It's hard to wrap your head around this because these particles started their voyage billions of years ago. Yet, the act of observation in the present can rewrite that journey. Our current measurements are, in a very real sense, shaping the universe itself. You might think this is just a wild thought experiment, but it has been tested. In 1984, physicists at the University of Maryland recreated Wheeler's delayed choice scenario on a tabletop. Using light sources and mirrors to create multiple possible paths, they confirmed that photons don't settle on a trajectory until measurements are made. The universe, it seems, doesn't commit until it's being watched. Does this mean the cosmos needs humans to exist? Wheeler argued not. Conscious observation plays a role, yes, but it's not the only way quantum possibilities become reality. Everyday matter, rocks, particles, energy, also brings the universe into being. Take a high-energy particle from radioactive decay, for example. Like photons in the double-slit experiment, it could travel multiple paths at once. But it only becomes real when it interacts with something, say a piece of mica. And crucially, it's the mica, not a human, that determines the outcome. The universe has its own way of collapsing possibilities into reality through ordinary interactions. In other words, the cosmos doesn't revolve around us. It has its own mechanisms for making things real. Yet, the mysteries of how it all works remain tantalizingly beyond our full comprehension. Our minds are limited, but our curiosity refuses to stop. We keep asking, exploring, and marveling at the universe. That's the wonder of Wheeler's vision. The universe is stranger, deeper, and more alive than we could ever imagine.